For the front part of your notes, there are situations and tables and graphs that all you get filled in. Read it and do it all. Do it without me. You are doing this entire front page without me. You are very capable. So we'll kind of brief on the first one, and if you're not done with the second one, we'll come to it in just a minute, or I'll just finish the minute. But this is the table and then the graph. Are we connecting the points?
No.
How come? Why is it discrete instead of continuous?
Because you can't have like
Yeah. This is talking about tickets. You don't sell half of the ticket to someone, you sell a full ticket. So since it's discrete, how do we write the domain and range? With that list. So 1, 2, 3, 4, 5, and then 10, 20, 30, 40, 50. Okay, how many of y'all still work on the second one? No? We're ready to go for it? So let's talk about the second one. So this one said to do what to continue the graph? Multiply by 2, so that makes it 80, 160, 320. And when it comes to the graphing part, are we going to connect these points? No, why not? It is discrete. It is talking about, well, it's talking about number of events. So people attending a number of events. So yes, same idea. We can't have part of an event. We can't have part of a person. So it's going to be discrete. Yeah, it could be a lame event, but you still have it, right? And you can't, I mean, you still have it, you just ended it early.
That's still
Right? Okay, so let's look at both these graphs. They're both discrete, so that's something they have in common. But what's something they don't have in common?
One's like swervy and then one's straight.
One is swervy and one's straight. What is it called when it's straight? It's a linear graph. Yes, it was the arithmetical, but this would be a linear graph. What makes it linear? The straight line, but what about the numbers makes it linear?
It's constant.
Constant of what?
It's adding.
Adding. That adding is making it linear. Now, we said this bottom one was curvy. What's the technical word we've been using for curvy? It is exponential. And what is making it exponential? Multiplying. The multiplying is making it exponential. It's making it have that curve. Okay. So we're going to practice all exponential, a lot of exponential today into the next week and a half. So if we go to the next page. On the next page, all of our exponential functions are going to be in this form. We talked about it a little bit yesterday with that paper cutting stuff. The first number, that A value, is always going to be, does anyone remember what that first part, that was 11 yesterday. What was the 11 referencing to? The first, that beginning, that starting amount, or your y-intercept. And then B, yesterday was 1/2. What was 1/2 in reference to?
It was constant. It
was that rate. We call it a rate, we call it a factor, we call it a ratio, different words all meaning the same thing though. That's exponential's version of a slope. Because it's not really a slope. Slope is a constant rate of change. This one is called the rate, a ratio, things like that. So if you look at our first example, it's just an equation. We are going to, so what we could do, we have two options because we're going to graph it. Option 1, we can replace that x with different numbers and do it by hand. Option 2, you have those nice graphing calculators. Let's get that graphing calculator helped out. After this example, you can come. Okay, so let's do this in our calculator. So, your calculator, go to the graph part. Are we here? Now we need to type the part after the equal sign, and we want it to look exactly like it does on the paper. So 3, and then our fraction of 1/2. And then raised to the power of x. Does anyone need help setting this part up? So pressing enter. There's the graph. Now, so on here, does anyone remember? So we need to graph it, which means we want to find the exact points we're putting on our table. Do you remember how to pull up a table? Anyone?
Menu.
Okay, we could go through menu. That's a little bit of a slower option. Faster option, control, and then the letter T. Okay, now here's our table. Did it tell us what x values we have to choose? Does the word, or does our problem tell you what numbers we have to use for x? Okay, that means we get to pick the ones that are going to fit the best for our graph we're given. Our graph, it's not limited to just positive x values anymore like we had yesterday. We could have negative if it would fit. So looking up, what would be the best number to start our graph with for the x value? What? Is that going to cover the whole graph if I use 1.5?
3. You just roll down.
Yeah, just scrolling around.
Yeah, start with 3 or 0.
What about this one? Would -1/6 fit on our graph?
Yeah.
Okay, then let's put that one. That's the highest point that's going to fit on our graph. That way we can get the rest on there. So if we have -1/6 and then 0, 1, 2, 3, 4.
Keep going.
It's okay. And then 3, 1.5, 0.75, 0.375, and 0.185. Are we okay with that part? Okay, so before we decide, well, is this going to be discrete or continuous? So how to decide? Were there any limitations that we were given for this problem?
No.
All they gave you was a word or was an equation. Since there are no limitations, it's going to be continuous. Now, before we connect it, what's happening to our y values each time?
It's getting smaller.
By what? By half. We talked about this yesterday. If it's getting smaller than that, or if it's getting half each time, what is it not going to get to? 0. We need to keep that in mind when we graph it. Because where y is 0, that would be this x-axis. So as we draw it, we want to try and draw it where it's not going under the x-axis, but getting really, really close to it. So it kind of like borders along the bottom. It's not actually getting to the x-axis, but it's getting so close it kind of looks like it is. There is always going to be a line for exponential graphs that the graph does not cross. That line is called an asymptote. Most times it's going to be our x-axis. We'll talk more about that on Thursday, but most times it'll be our x-axis, so there's always going to be that line that the graph is not allowed to cross. Okay, so let's do the domain range part. Domain, did we have any restrictions for our x values? No, so if there's no restrictions, what do we write? All real numbers. That also had the negative infinity, less than x, less than infinity. That was the same thing as all real numbers. Or we could shorthand that all real numbers to R. All those look familiar? They all mean the same thing. You don't have to write all three. Pick one and write it. Now for the range. Were there any limitations for the y values? Yes. What's going to be true about all the y values? They all have to be positive, and they're not going to get to 0, so y values are greater than 0. Okay. So let's go to the next one. On the next one, we are going to graph it again. We're going to get it all set up. So let's go ahead and put it all in our calculator, ready to go. So if we're starting with -2, that makes it 1.6875. All right, and then filling it in our table. Okay. And then we're connecting it. Can you tell what the graph isn't going to get to? Look up in your table, look down in your table. What is that graph not going to quite reach? Is it getting bigger as you move down?
Yes.
Okay. And as you move in that negative direction, like if you go up on your table, what's happening to the numbers?
The numbers are getting really, really small.
They're getting really, really, really small, but what are they not quite getting to yet? 0. So it's that same situation that we had before, where they're not going to quite get to 0. So we don't want to draw that graph underneath that x-axis or even touching it. Again, there were no limitations, so it's continuous. What about the domain? Are there any x limitations? The x values?
Oh, no.
Farthest left, farthest right? You got to pick whatever you want for the x values. So what am I going to write for that? All real numbers, or negative infinity, less than x, less than infinity, whatever one you choose to write, any of those three options is fine.
The days are.
And then what about the range? Are there limitations for y values? Anything bigger than 0. So y is greater than 0. Now, before we move on, there's some similarities with our graph. They're both continuous. What's another similarity? They both have all real numbers for the domain. Y is greater than 0 for the range. What about something that's different about them?
Oh, one's negative one.
Okay. Which one are you calling the negative one? The top one. That is going down. That is called an exponential decay. And then the bottom one, as it's moving up, that is called our exponential growth. Now, anyone want to have a guess of what affects the growth or decay? There is a number that affects it. That number that has the parentheses. What is going to make it decay and what is going to make it grow?
Yeah.
Everyone collectively mishmashed and said the same thing. Yes. If it is less than 1, it's going to decay. If it's greater than 1, it's going to grow. That rate is always going to be positive, though. Because if it was negative, your graph would be going up and down all over the place. So it's always going to be positive. It's just if it's less than 1 positive, it's going to decay. If it's more than 1 positive, it's going to grow. Alright, so let's go to the other page now. So on this page, we're going to look at the top part. Number 1 through 4. It's a table, and we're trying to figure out from the table, is it linear or exponential? How are we going to know the difference?
If it's multiplying or adding.
Right. Is it adding for linear, or is it multiplying for exponential? That's going to give the difference. So if we look at number 1, what's happening, and this is talking about the y value. So what's happening with the y values? Are they adding or multiplying? Dividing by 2, but that means multiplying by a half. So that would make it exponential. Then on number 2, what's happening with those y values? It's subtracting 2, which is the same as adding a negative 2. So still adding, so linear. What about number 3? It's adding a half each time, so that would make it linear. And then number 4 is doing what? Dividing by 5, but that's the same as multiplying by a fifth. Yep. Okay.